Alright, so let's start talking about the homework you had from yesterday. So in number 2, you got 1 over 2,608. In number 3, so again, you could have done this either way. Initially when I did the worksheet, we didn't learn the sine inverse formula, but you could have done this using sine inverse. Either way, you got 1 over cosine of a half. Number 4, you should have gotten negative 1 over 2 sine 2. Number 5, you should have gotten 9 over 973. And then, I apologize, I meant to tell you to skip number 6. We are actually learning natural log derivatives this coming week. 7 was 1/9. 8 was 1/16. Sorry guys. Let me go back to normal. Okay. 9, you got 1 over 0.221. 10, you got the cube root of 196. 11 had an E, again skipping. And 12, we used our table and got negative 1/2. 13 for A and B, also using the table, you got 2 and 6. At the top, you should have gotten 2 answers for a lot of these problems because the unit circle occurs at 2 points. Now, when we talk about arc, their arcs can't live at both of those 2 points. So again, some of us might have had 4π3 and 5π3. However, we have to eliminate 4π3 from our final answer because the arc sign can only live in quadrant 1 or 3. Same with over here, the arc cosine can only live in quadrants 1 or 2. So we once again eliminate 4π3. So showing you where they could occur, however, you have to take into account the restricted domain of the inverse. So you get rid of 4π3 from both 2 and 3. So if you had that, make sure you understand why, and as well as 2, sorry. Make sure you understand why they don't actually exist there. Okay, number 5 was 4/5. Number 6, 12/13. Number 7, square root 17. 8, square root 2 over 2. 9, 1 over the square root of x squared plus 1. Then I'll give you a second to check 10, 11, and 12. Okay, and then on the back, we had our inverse trig derivatives. So 13 negative 3 over square root 1 minus x squared. 14 2x over square root 1 minus x squared minus 1 squared. 15 16 17 18 19 was the same as 15, just wrote different, and 20. Okay. So hopefully you are feeling much better about inverse trig functions, about inverse functions in general. We've now been focusing on them for almost a week, and we've concluded kind of our study. I do want to do one kind of wrap-up activity with you and sort of a culminating activity to make sure we are totally 100% getting each of these. And then we're going to actually start lesson 3.9, which is exponentials. So let me get my document camera plugged in. So again, take a minute and try the 4 derivative of inverse functions on that page. just a few more minutes on that, and then we'll go over them. Don't understand why it's inverted. All right, so the answer to number 1 is B. So we get that by doing the following. So in number 1, what you have to do is take into account the x and the y's. So it's asking for f inverse prime at 2. So that's like 1 over f prime. And you have to go back to your original idea. And if it's asking me for f inverse prime of 2, then that's like 1 over f prime of 1. So if it's asking me for f inverse prime of 2, that's like 1 over f prime of 1. So I need f prime of x. And then I need f prime of x at 1. Which is 8. So I get 1/8, which again is option B. Okay, number 2 says if f of 2 equals 3 and f prime of 2 equals 4 and g on f are inverses, then write me the equation of the tangent line to g of x at x equals 3. So g of 3 would be the inverse of f, so that would equal 2. So then I need g prime of 3, which would be 1 over f prime of 2, which is 1 over 4. So the equation of my tangent line is y minus 2, 1/4 x minus 3, which is option D. Next up, number 3, if f of x equals 3x squared minus x and g and f are inverses, then g prime 10 could be which of the following? So what we have to do is take into account, when does f of x equal 10? So you have 3x plus 5 and x minus 2. So it gives you a negative 6x and a positive 5x, which gives you a negative x. So we get x equals negative 5/3 and x equals 2. Now in actuality, f of x does not have an inverse because it is an x squared function. However, finding these 2 points, we're going to see that g prime of 10 could only exist at one of them. So even though it begins as 2 possible, it can actually only end up being 1. So what this means is g prime of 10 could potentially be negative 5/3, and g prime of 10 could potentially be 2. So then we need to also take into account what the derivative is at those 2 points. So I need to know what is f prime of 2. So I can find g prime of 10, etc. So we know that g of 10, there shouldn't be primes on this. And we also know that so that's what we've gotten from this information. And I wanted to summarize just so I could erase the remaining part of my screen. We know we're going to need the derivative. So f prime of x is 6x minus 1. So now I need f prime of 2 and f prime of negative 5/3. So we get positive 11 and negative 11. So if you go back to your rule, g inverse prime of 10 f inverse prime of 10 is really the same as g prime of 10, which is the same as 1 over f prime of 2, or 1 over f prime of negative 5/3. So that's 1 over 11, or 1 over negative 11. And only one of those 2 answers exist. So that's why I said, guys, why don't you tell me it's sleepy? Okay, so only one of those 2 answers exist. And the answer that exists is the example that is a positive which is f prime of 2 or 1 over 11. So I feel like I told Nick that you would never have one that's like 2 answers, and then lo and behold, I pick a multiple choice one that has that type of concept in it. Okay, so that was answer E. And then last one we're going to look at is answer choice number 4. So let's talk about number 4. We have g of x equals x cubed plus x plus 1. H is the inverse of g, and we want to find h prime of 3. So that's really like saying h g inverse prime of 3, which is really like saying 1 over g prime wherever the original function has a y value of 3. So what I have to do is set 3 equal to x cubed plus x plus 1. And that one's pretty easy. I can actually just look at that and say, oh, if I plug 1 in, 1 plus 1 plus 1 is 3. So my x value is 1. So that means h prime of 3 equals g inverse prime of 3 when we have 1 over g prime of 1. So I need g prime of x, which means I need g prime of 1. Which is 4. And my answer is choice D. Alright, so what we're doing today is actually going back a little bit and looking at basic kind of exponential and logarithmic function rules. So on that single sheet of paper by itself, I kind of gave you a wrap-up of all of the rules. So all of those rules are a general idea of what we need to know in order to find an inverse function. And then what we are going to do in here is find inverse derivatives. But in order to be able to find inverse derivatives, we actually need to know how to find values of exponential and simplify exponentials. It's important to also recall that if you have an exponential raised to 0, it's equal to 1. So if you have any power, so if you have like a to the 0 or 2 to the 0, anything to the 0 power is 1. Anything to the 0 power is 1. So that's just like a side little note. I don't think it's on your roll handout, So I just want to reiterate, anything to the 0 power is 1. The second rule I want to reiterate is our change of a function from one form to the other. So if you have a log in the form a to the x equals y, we can rewrite that as a to the y equals x. Or if you have e to the x equals y, you can rewrite that as ln y equals x. So what we want to do is evaluate a function such as the log of 3 to the 81. So that's kind of equal to this imaginary y right now. So what we're trying to determine then is if we transform this to the other form, this is the same as saying 3 to what power is 81? So that's the same as saying 3 to what power is 81? So 3 to the 4th power is 81. Therefore, the log base 3 of 81 is 4. So in example B, that's kind of like saying, okay, 25 to what power is 5? Twenty-five to what power is 5? So that would be the 1/2 power, because the square root of 25 is 5. So 25 to the 1/2 power would be 5. Okay, how about log base 10 of 0.001? So back in the day, this was one of the only bases you could actually do because our calculators used to only be able to do log base 10. Now the newer calculators can do multiple logs. But once again, this is saying 10 to what power is 0.001. So we know that if 10 has to equal a decimal, that 10 has to actually be a fraction. So that's kind of like saying 1/10 to the y has to equal 1/, and then you'd have to know what 0.001 was as a fraction. So if you go back, 0.1 is 1/10, which means 0.01 is 100th, which means 0.001 is 1,000. And then going back to our basic ideas, we also know that y squared, or 10 squared, will get you 100. So you need another one to get you to 1,000. So 1 over 10 cubed will get you 1 over 1,000, which means in terms of this problem, my answer needs to be -3 because it can't account for my fraction. So when that y moved to the denominator, it needed to kind of be understood. It needed to now be negative. And then ln of e to the -100. This one might be the easiest of all if you remember your inverse rules. Ln and e are canceling properties because they're inverses of each other. So that's really just -100. If you forgot that they canceled each other, you could treat that -100. It comes down in front. So anything raised to a power inside a natural log can come down in front. And then you'd have the natural log of e now to like the first power. And again, hopefully that allowed you to see the ln and e canceling. We have properties of logarithms, and those properties are that you can add, subtract, and change those back to multiplication or division. So we can take logarithms that are written out as long logs and rewrite them as single logs. So since their bases are the same, log base 4 of 2 plus log base 4 of 32 is log base 4 of 2 times 32, or log base 4 of 64. And now you need to ask yourself, 4 to what power is equal to 64? So that I can get my final singular answer of 3, because 4 cubed is 64. Letter B, log base 2 of 80 minus log base 2 of 5. Subtraction turns to division. So you get log base 2 of 80 divided by 5. So 80 goes into 5 16 times. So it becomes the question of 2 to what power is 16? Which is the fourth. We can also use properties of logs to expand a quantity. So we can also use our properties of logs to expand a quantity. So division inside those parentheses turns to subtraction. something raised to a power can become the coefficient out in front. And multiplication inside a natural log turns to addition. So that's ln 3 plus ln x squared minus, and then you can bring that 5 out in front, ln x plus 1. Now addition within a natural log doesn't simplify, only multiplication. And just like we brought this 5 from up above here, we can do that to the 2 as well. It's important to make note that the natural log of 3 would be considered a constant. The natural log of 3 is considered a constant. That is simply a number. So again, ln 3 is a constant or a number, where this and this are considered functions. So we can also take natural logs backwards. So just like you could simplify a log, you can also simplify a natural log. So the first thing I'm going to do is move my coefficient out in front back in as an exponent. And the natural log of 8 to the 1/3 power is actually 2. So I get ln 3 plus ln 2. And 2 natural logs being added is the same as multiplying their insides. So you get the natural log of 6, which again is a constant. That's different from example B, where you have the natural log of x plus the natural log of y to the a minus the natural log of z to the b. So we brought the coefficients out in front in as powers. We're going to change addition to multiplication. And then we're going to change subtraction to division. So we get the natural log of xy to the a all over z to the b. Example number 1 for solving now. So now we're changing our priorities and we are solving for x. So how do you get rid of a natural log? You need to use its inverse. So the natural log and e are inverses. Hence why we learn this after we learn inverses. So the natural log and e are inverses, just like sine x and sine inverse theta are inverses. The natural log and e will simplify each other. So if I e both sides in example 1, e to the ln cancel because they're inverses. That's like saying 1/2 times 2. Those are known as multiplicative inverses from way back in the algebra days. So, e'ing both sides gives x equals e to the 5th, which is in fact my solution because e to the 5th represents a number. You could plug it in on your calculator and you'd see that that means x is approximately 148.4132. Again, remembering to give me at least 3 decimals if you're going to use a calculator and get a calculated answer. But again, the calculator is an approximation where e to the 5th is the actual answer. So again, you're comparing an approximation to the actual. We can e both sides even when ln has stuff inside its fraction. That just makes this 5 minus 2x equals e to the negative 3. Once again, solving for x, we get negative 2x equals e to the negative 3 minus 5 all over negative 2. So cleaning that up, e to a negative can't happen. So you get negative 1 over 2 e to the 3rd because we drop the negative exponent down and move the negative up. And then here, a negative divided by a negative gives a positive 5/2. And again, if you really cared about what that is, on a calculator, that is approximately 2.4751. Okay? It gets a little trickier when we have 2 natural logs, which gives me 2 x values. So kind of like quadratics and absolute values, you got to get like all the ln's on one side to a single absolute value and all the other stuff away. So we're going to add that ln x to both sides. Then we're going to apply this property of logarithms that say adding 2 natural logs together is the same as multiplying their inside stuff. But we don't want all that fractions and fractions, so we're going to distribute that x. So we get the ln of 2x squared plus x equals 2. So we're going to e both sides. And now that makes this a quadratic. And we know that in order to solve a quadratic, it's got to be set equal to 0. We know this isn't going to function. E squared is never going to give me 1 in the middle. So if something's a quadratic and not factorable, we have to solve by using quadratic formula. So I'm going to use my extra space up here to say x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Since we obviously can't multiply 4 and 2 and negative e squared, this would become a calculator problem. Then we'd get our two potential roots. But only one of these can actually be the answer. And the reason for that comes from the domain of a natural log. And the domain of a natural log of x says that all x values have to be greater than or equal to 0. We can't take the natural log of a negative. So this answer here gets canceled out because we can't take the natural log of a negative value. So even though when we simplified, we end up getting this x squared value, and that would make that positive and greater than this, because the original contained a natural log of x, we cannot utilize it. So that makes x equal 1.6883, my solution. Just like e's get rid of ln's get rid of e's. So we can ln both sides in this example, leaving me with 5 minus 3x equals the natural log of 10. So you get negative 1/3 natural log of 10 plus 5/3. And if you wanted to get super fancy, or it would help you, that negative 1/3 can actually come in as an exponent of the 10. So again, you could type this in on a calculator, and we get that x is approximately 8991. Once again, we can't ln both sides until e is isolated. So I have to move that 7 over before I can ln. And again, you could keep it as one singular fractional answer or break it down by dividing the ln and 3 both by 2. And once again, you could approximate this on a calculator, and you get negative 0.527. So in this one, I have multiple e's that I'm not going to be able to isolate. This is actually a case of using a quadratic factoring method to solve. So what I'm going to do is rearrange my terms or substitute out my terms so you can see what I mean by a quadratic. So what we're going to do is, for reference purposes, we're going to say that e to the x is really u. So that becomes 7u minus e to the 2x. Well, we know that e to the 2x is really like e to the x times, or raised to the second power, because the way two things being multiplied works for exponents is you multiply them to get a power to a power. So that's really kind of like saying e to the x squared. So we're going to make this u squared equals 12. So now this looks like a quadratic from back in the days of algebra. So we're going to get it set equal to 0 by adding u squared, subtracting 7u, and leaving the 12. So factors of 12 that sum to negative 7 are negative 3 and negative 4. Which gives u equals 3 and u equals 4. But u isn't really u is e to the x. So that means e to the x equals 3 and e to the x equals 4. But we don't want our answers in terms of e to the x, we want them in terms of x. So we'd ln both sides. And we get x equals ln 3 and x equals ln 4. So our homework is a little bit of a mixed variety today. So what I want you to do is complete that inverse trig function worksheet that's in your 3-9 packets, as well as look at some of these problems on our textbook page. So you're going to do the 3.9 quick review and 1, 3, and 5, and that's all on page 170. And again, that is typed out on Fusion for you.